Greetings everyone, welcome back into Calc 2. Time to finish up our discussion of advanced integration. We're going to do this last topic of integration here, which will pretty much take care of some of the weird occurrences and weird limits that you can get. We're talking about improper integrals. Now an integral is improper anytime it's bounded or unboundedness is in question, if you want to think of it this way. Okay, there's really two main ways that this can happen. One, you can actually have infinity as one of your boundaries. I use that loosely with the term infinity, of course, because infinity implies that it is unbounded. So of course that brings into question the viability of the integral itself as to whether or not the answer is unbounded. Notice I'm careful to say unbounded and not infinite, right? We're not actually going to use infinity as an answer here. That is improper. Okay? There's all different kinds of infinities out there. It's better just to say that the answer to an integral is divergent or unbounded whenever it is quote-unquote infinite. Okay? The other way that this can happen is if you have an interval that looks normal, but somewhere in that interval is something that causes a vertical asymptote, right? For example, here, the 0 would be bad for 1 over x squared, okay? But any interval that contains that value would have the same issue. Okay, in this case it happens to be one of the boundaries, but if that 0 were anywhere in the interval, it would still be the same kind of improper, and we would have to deal with that. Okay, so just like any of the things that we've done since Calculus 1, the way that we approach, pun intended, the way that we treat things that are potentially unbounded is we use limits. Limits are the only calculation that we have where it's okay to write infinity as either the boundary or the answer. And that's because limits treat infinity like what it is, something that is unbounded. Okay? Infinity is just a symbol here, and it's a symbol for you need to elaborate. Okay? Same thing with one of these other boundaries like 0 here. If it's causing some sort of infinity inside of the range, which is what a division by 0 will do, right? A vertical asymptote will do, then it needs to be treated with the proper language. And that's why we have limits, so that we can talk about these things properly. Hence the name improper integrals until we fix them. So here's what you do. Instead of infinity, or instead of the number that's causing the infinite output, right? Either way, I'm going to put a letter there, A. You can use B, you can use C. Those are the typical things that we use. You could go Greek also with the, gamma, alpha, beta, those sorts of things. We tend to avoid Y's and X's and Z's because those are going to be our function counters. T's also. You got to be careful with a few of these things. Okay? So I'm just using A in both of these examples. And what happens is you don't actually have to work the integral itself any differently than what you're already accustomed. It's going to be any type of integral. Sky's the limit. You just need to be able to perform the antiderivative, right? Use the fundamental theorem of calculus, top minus bottom, top value minus bottom value. It's just that one of those two values, or possibly both, it's possible to have negative infinity to positive infinity. That's also a strong thing. But here, what's going to happen is you're going to do everything the same, but one of your boundaries is a variable. And after you're done evaluating that, the limit will kick in, and you can then see what the limiting value of the answer is. Once you have the limiting value of the answer, then you can determine if the integral truly exists or if it's unbounded or divergent. The word that we're going to use from now on out is divergent. And that's one of the things, one of the terms that you need to get used to for one of the units that's coming up next on sequences and series. Anyway, divergent is a very common word for some sort of limit or sequence or list that has infinity, or rather an unbounded nature to it. Okay, so convergent would mean that there's an actual number that this thing can equal to, like 6 or 8 or 10, -4. Those would be convergent integrals, and that's what you're accustomed to. They converge to something. Okay, but these can be divergent, which means the answer is unbounded or infinite. Okay, that's what it implies for these things. That's what the divergent implies. Okay, so let's actually perform this thing here. The limit as a goes to infinity of the integral from 3 to a of 1 over x squared dx. Well, of course, I'm going to perform the integral the same way I would in any other case. I'm just going to treat this as x to the -2 power. So I have the limit as a goes to infinity of the integral from 3 to a, x to the -2 dx, which would become the limit as a approaches infinity of -1 times x to the -1 evaluated from 3 to a. Okay, which of course this is the limit as a goes to infinity of -1 over a, right? That's when I plug in a to the -1 times -1, that's -1 over a. And notice that that's the only place where the a is going to show up. When I plug in the 3, that's just going to be a number. And the limit of a number, the limit of a constant, is always that constant. Okay, so then fundamental theorem of calculus, subtraction, top minus bottom, right? I'm going to plug in 3 here, and I'm going to get -1/3, like so. Okay, so then right here, I'm going to notice that I have the limit as a goes to infinity of -1 over a. And this limit right here has the value of 0, because the denominator here is unbounded while the numerator is staying at 1. So I'm going to have 0 minus -1/3, and I'm getting a value of 1/3. So the fact that I got a numerical answer other than something unbounded or infinite means that this is a convergent integral. Okay, so if there's a question of what does it mean for your integral to be convergent, this is what it means. Okay, for what we're implying, for what we're doing here, it is convergent if you can show that it actually equals a bounded answer, right? Something non-infinite, something bounded. Okay, so this one here, same idea. I have to convert the improper notation, which in this case is I can't actually use 0 as a function value. And that's what's improper about this particular whole process. I can't use infinity as an input. Remember, we don't write f of infinity when we're doing function notation. That doesn't make sense. That's considered improper because infinity is not a value that's obtainable, right? Instead, we use limits to approach infinity. And it's the same thing here. I wouldn't write f of 0 if 1 over x squared were my f function, right? Because that would be undefined. It would be improper to use. So same idea. I'm going to use a limit to approach 0, but notice there's something slightly different here. I'm approaching 0 from the right only, okay? If the 0 had been the top limit, it would be from the left. Since it's the bottom limit, it's from the right. think about that for a second. This is a lower x value. This is a higher x value. So if I'm approaching 0 from the higher to the lower, technically on the x-axis, that's from the right. I'm approaching 0 from the higher end towards 0. So it's from the right only. Okay? Whenever you have these kind of limits where it's an x value somewhere in the interval, then you have to actually set up properly the limit from the left or from the right. And that may actually make the difference in some of your calculations as well. Okay, same idea as before though. I'm going to use x to the negative 2 power again. So I have limit as a approaches 0 from the right, antiderivative integral from a to 3, x to the negative 2 dx. I then perform my antiderivative, so I have limit as a approaches 0 from the right of negative x to the negative 1 from a to 3. And of course, when I plug in the 3, I'm going to get negative 1/3, right? That's the top. Minus, now I'm incorporating the a, so I bring in the limit. Minus the limit as a approaches 0 from the right of negative, okay, so I'll go ahead and double up the negatives to get the positive here because of that negative. 1 over a. And then I need to actually consider the value of this limit here. The limit as a approaches 0 from the right of 1 over a. Okay? And that's one of those basic limits that you need to know. From the right of the 1 over the reciprocal function, remember, if I have the function 1 over x, that's the graph of this right here, the baseball function I call it. And from the right, it's doing this. It's approaching positive infinity. So the value of this limit is positive infinity. Okay? So then I don't actually have a solution. I don't have an answer to this integral. Okay? We would say that it is divergent or unbounded. Okay? Quick and dirty answer is that the integral is trying to add up an infinitely sized area. The true language, though, is it's an unbounded area. You can see it's stretching up to infinity this way, and the curve doesn't close in on the axis fast at all and allows it to just flow up to infinity forever and just becomes unbounded. And I know you might say, well, wait a minute. This flows to infinity also, and yet we got an answer for this one. And it's true. The curve is approaching the axis fast enough that it closes in and actually has a bounded limiting value. One of the things that you can chalk up to our crazy number system here is the fact that some things that seem infinite can actually have a finite total, and other things that seem infinite really are unbounded. Okay? Which is why we have to be able to check and calculate all of these different things the way that we do. So let's get some examples of all of these different things now. Here's a visual better than the one that I could draw on the board of the function 1 over x squared. Here in blue you can see it's that volcano shape around the y-axis. And the integral from 3 to infinity happens to be 1/3, right? Which is this section right here. And as you can see, it hugs down to the x-axis pretty quickly. Whereas it even lists the integral from 0 to 3 as the value infinity. It is an unbounded integral. As you can see, this particular part of the graph does not hug as quickly as the other one. If I were to shrink this down, right? You can see something like 7, 8, and 9 over here, whereas the 7, 8, and 9, you can see it's just not getting close to that axis as quickly. So it's going to be an infinite integral when you do this section right here. Let's start off with some examples that just use substitution. So I have the integral from 5 to infinity of x over the cube root of x squared plus 3 dx. And of course it's improper because it has an infinity as the upper boundary there, or rather unbounded upper boundary, right? So I'm going to use a limit, right? I've got the limit as a approaches infinity of the integral from 5 to a of x over the cube root of x squared plus 3 dx. And of course, the actual integral itself requires a basic substitution where I will be letting u equal to x squared plus 3. Therefore, my du is going to be 2x dx, which all I have is an x dx, and I'm going to have to multiply a 2 here and balance it out with a 1/2 out here. If you wish, you can also put the 1/2 outside of the limit. It doesn't matter. It passes in and out of both the integral and the limit. So now I can actually do my substitution here. Okay. So now I'm going to still have my limit as a goes to infinity. I've got my integral here. Now I'm going to be careful with my limits because remember, these are x numbers, right? These are numbers that get involved with x. So if I plug 5 into x, 5 squared is 25 plus 3 is 28. And right here, if I plug in a for x, I'll have a squared plus 3. Right? That's what the u value is going to be when x is a. And what I've got at this point is u to the negative 1/3 du. Let's look at that real quick for a second. Because remember, I let u take the place of this piece here, which means I have the cube root of u in the denominator. So cube root 1/3 power in the denominator makes it negative exponent. And I just did this so that I can quickly get to my power rule here. Okay, so then I've got my limit as a goes to infinity of, whoops, I've been known to make this mistake before, and I'm hoping all of you caught me again. The 1/2. I forgot to bring my 1/2. So 1/2 is multiplied out here, which means I'll just put it right here. Yeah. And then I've got u to the 2/3, right? Because that's the 1 plus negative 1/3. And then of course it's going to have to be times 3/2 to finish up that power rule there. And this is going to be evaluated from 28 to a squared plus 3. So then I've got 3/4 times the limit as a goes to infinity of a squared plus 3 to the 2/3 power minus 3/4 times 28 to the 2/3 power. Okay, so I've just done top value minus bottom value, right? Fundamental theorem of calculus there. And I'm going to look at the limit first before I try to even venture what this is going to simplify out to be. because this is going to really determine whether I need to try or not, right? So the value of this limit right here, let's take a look. If I let a become unbounded, it's to a positive exponent. Even though it's 2/3, which will slow this down, it's in the numerator, which means as a becomes unbounded, this whole value is going to keep growing and growing and growing. The value of this limit is infinity, right? Which means that I've got a divergent answer. Or unbounded, right? Okay. Next example. Again, it's improper because I've got the infinities in here. There are, different schools of thought that people will, kind of mention here and there. Some people will say, well, since, we're doing the infinities in the same problem, you can just pick one letter and do a and negative a. Other people will say, no, we need to treat those infinities separately so that we can have full control of this integral. I'm just going to do it the most generic way, and if you find an intermediate way that makes more sense to you, of course you can build on that. The generic way would be to find a number somewhere in between these two unbounded values, right? That is in the domain, which of course the domain of this function is all real numbers anyway. I'm just going to pick 0, okay? And then I'm going to split this integral into two integrals, okay? From 0 to a of e to the x over 1 plus e to the 2x dx, plus integral, and I'll use b this time, to 0, e to the x over 1 plus e to the 2x dx. So what I've actually done, you see, is split this one integral over a common boundary, which, we do all the time with different integrals. You split over a domain value. If you've got, some function and you want to integrate one piece of it one way and another piece of it another way, right? You pick some boundary value and you split the integral into two integrals, where one does some of the integral and another one does another piece of the integral. So I just picked a number in between negative infinity and infinity. 0 seemed like a nice center. It doesn't really matter which one you pick. And then, of course, notice I've used a and b instead of infinity and negative infinity, because I'm going to be setting up limits here. Limit as a goes to infinity, and limit as b goes to negative infinity. Okay? Now, of course, the splitting over the value might be overkill for this integral, but this is the most that people typically do. So I'm just going to be as generic as possible, and then you can make your own understandings and patterns for your own sake. Okay? So now I'm going to perform each integral separately. Although across both of them, I'm going to use the same substitution, so I might as well go ahead and do both of those. Notice that I'm going to let u equal to e to the x, which means du is going to be e to the x dx, which I actually have e to the x dx, right? You can see that I do have that one, and that's just going to give me 1 plus u squared in the denominator. Okay, so then here's what I get. Limit as a goes to infinity of the integral from, now be careful, when x is 0, u is 1, right? Okay. And then when x is a, u is e to the a. And then I've just got du over 1 plus u squared plus limit as b goes to negative infinity of the integral from, and of course this is going to be e to the b up to the 1, right? And again, the split should be the same, right? Because I'm using the same u variable for both of these. And I'm getting du over 1 plus u squared. I'm hoping that you recognize that particular antiderivative. What we end up with here is the limit as a goes to infinity of arctangent, inverse tangent of u, evaluated from 1 up to e to the a, plus the limit as b goes to negative infinity of the arctangent of u, evaluated from e to the b up to 1. All right. So now substituting, I have the limit as a goes to infinity of the inverse tangent of e to the a minus inverse tangent of 1. Don't really care about what that value is right now, because in the very next step I'm going to have plus inverse tangent of 1. And as you'll notice, these two are just going to zero out. And then I have minus the limit as b goes to negative infinity of inverse tangent of e to the b. Okay, now don't do the same kind of thought process. These two add out to 0, but these other two do not. Okay, this right here, as a goes to infinity, e to the infinity, basically, right? E, an unbounded e to the x, is also infinity. Okay? So we're basically doing the limit as some value c goes to infinity, inverse tangent of c. Okay? Now you're supposed to remember that inverse tangent has an upper boundary as its input value goes to infinity of pi over 2. Okay, and then over here we have e to the negative infinity, basically, which means that I have minus the inverse tangent of 0, basically, because I'm just doing the limit as b goes to negative infinity of e to the b. That limit of just e to the b is 0. And then inverse tangent of 0 is also 0. Therefore, final answer is pi over 2 to that particular integral. Okay? So that one seemed like it would be extremely divergent, right? It had all kinds of infinities everywhere, but it actually was convergent. It converges to pi over 2. So let's take a quick look at these two functions. First, we have the x over cube root of x squared plus 3. Looks a lot like a cube root function, just has a slightly different shape because of the x squared there. In any case, we have a integral here from 5 to infinity, which it claims is infinite. And as you can see, that would be completely true. If we started at 5, this thing just keeps on increasing forever here. So if I try to integrate that piece right here, we're just going to get something that's just going to keep growing and keep growing. All right. Then if I take the function e to the x over 1 plus e to the 2x, we have something that has this, hill in the middle. Kind of reminds you a little bit of a bell curve, but it's not exactly the same function as that. And if you integrate from negative infinity to infinity, notice the whole inside is shaded in there. And it gives you the value 1.57, which is an approximation for pi over 2. Next, a couple of examples using the advanced integration techniques that we've also been talking about in this unit. The integral from 1 to infinity of 8 dx over x squared plus 4x. Okay, so if you haven't recognized it right away, this one can either be done with partial fractions or with trigonometric substitution. I'm going to do it with partial fractions. Okay, so here I go. I'm going to, of course, first convert this to a proper setup. The limit as a goes to infinity of the integral from 1 to a of 8 over, and then I'll go ahead and factor this out, x times x plus 4, right, dx. Now I'll have to go through my integration separation technique, right, partial fractions. So I will set up my equation here. 8 over x times x plus 4 is equal to a over x plus b over x plus 4, which I will then multiply, right? I'm going to multiply and get the equation. When I multiply the common denominator here, I'll have the equation 8 equals a times x plus 4 plus b times x. And if I let x be negative 4, then I will have 8 is equal to negative 4b, which tells me that b is negative 2. And if I let x be 0, I will have 8 is equal to 4a, which tells me that a is positive 2. Okay, so now I can reset up my integration here. I have the limit as a goes to infinity of the integral from 1 to a of 2 over x minus 2 over x plus 4 dx, which I will get the antiderivatives using logarithms here. So limit as a goes to infinity of, I'm going to factor the 2 out of both of these out front here. 2 is here. So 1 over x, antiderivative is ln absolute value x minus ln absolute value x plus 4. And this is from 1 to a. Okay. Of course, I can make this a lot easier on myself, and also the limit itself much easier to deal with if I use my logarithm rules here. So then this is going to become 2 times the limit as a goes to infinity of the ln of the absolute value of x divided by x plus 4. And then, of course, this is going to be evaluated from 1 to a. Okay, so I'll plug in the a. I'll have 2 times the limit as a goes to infinity of the ln of a over a plus 4. All right. Minus 2 times the ln of the absolute value of 1 over 5, right? Because 1 plus 4 there gives me the 5 there. Okay. Now here, notice to evaluate this limit, I can make it much easier on myself if I just look at it this way. It's really 2 times the ln of the limit as a goes to infinity of a over a plus 4, like this. Because that's an easier limit to look at. Whenever you have a going to infinity and these are tied in power, remember you just use the coefficients. That's going to be 1 times a right here and 1 times a right here. What I've really got is 2 times ln of 1, which ln of 1 is 0. So this whole thing goes to 0. This piece right here, right, is 0. Which leaves me with negative 2 times the ln of 1/5. And to make this a little bit easier to look at, I'm going to use another logarithm rule which says I can bring in a coefficient of negative 2 as an exponent. So that's ln of 1/5 to the negative 2 power, which is ln of 25. So we have a convergent integral there because we actually got an answer value, ln of 25. Okay, next, the integral from negative infinity to 1, 5x squared e to the x dx. Okay, obviously an integral that I'm going to have to do by parts because I have the repeater type of pattern times the terminator type of pattern, right? I've got a polynomial times an exponential, which is going to be an easy chart method, right? Tabular method by parts. First, let me correct the improper setup though. So this is going to be equal to the limit as a goes to negative infinity of the integral from a to 1, 5x squared e to the x dx. And I want you to note that it'll be easier if I just pull the 5 out like so. And I just do the integral of the x squared e to the x there. Okay, so I'm going to set up my tabular method of integration here. I'll have my u and my v. My u is x squared, my v is e to the x. So then I will do derivatives here, 2x, 2, and 0. Integrals to match, e to the x all the way. Easy enough. And now I'll be doing my multiplications. So I have x squared times e to the x. So here I go. Equals, and I have 5 times the limit as a goes to negative infinity of x squared e to the x. And then I've got 2x times e to the x, but remember they alternate, right? So I have minus 2x e to the x and plus 2e to the x, like so. Okay. So now I've got 5 times the limit as a goes to negative infinity of, I'm going to factor an e to the x out. Oh, I forgot. This is from a to 1, right? So let me go, I'm still going to factor this out though. I have x squared minus 2x plus 2 here. And that's from a to 1. Okay. So plugging in the 1, right, doesn't require the limit. I'm going to get 5 times e, because it's e to the 1. And then that's times 1 squared minus 2 plus 2, right? So times 1, basically. Minus 5 times the limit as a goes to negative infinity. And then I'm going to do a little manipulation here. I'm going to write it as x squared minus 2x plus 2, but not x though, David, come on, it's not x's anymore, I plugged in a, over e to the negative a. Now look at what I did here. What I did was I moved the exponential to the bottom by making it have a negative power after I plugged in the a's. And the reason for this is because I was getting an infinity times infinity setup. Remember, the infinity times infinity is one of those inconclusive formats that you would have learned about in Calculus 1. And if you're still unsure about that, you can go look at my video on L'Hopital's rule, which is what I'm about to employ here. By doing this particular switcheroo, notice now what I'm getting is infinity over infinity, which allows me to use L'Hopital's rule. Okay? This particular piece is finished, 5 times e, that part is done. However, this particular piece right here, I'm going to do a couple of levels of L'Hopital's rule. First, it would be the limit as a goes to negative infinity of 2a minus 2 over negative e to the negative a. Because remember, I would be doing the derivative of the top and the bottom separately. In this case, a being the variable, so I do the derivative with respect to a. And again, if I plug in negative infinity, I still get an infinity over infinity situation, okay? Because if I plug negative infinity into this negative a, same thing as up here, I'm getting e to the infinity, so I'm getting infinity over infinity here, okay? Now, oh, I'm sorry, you know what? I misspoke. This is a 0 times infinity situation. My apologies there. I should have been more specific. E to the negative infinity, right, would be 0. And then these would be infinity here. So it's still indeterminate form that leads to a L'Hopital's rule. I just wanted to be more precise there. Okay, this again can be used with the same L'Hopital's rule. So then this limit becomes the limit as a goes to negative infinity of 2 over e to the negative a, which I'm hoping that you'll see is really 2 over e to the infinity, because I'll get a double negative when I put the negative infinity or a very large unbounded negative number into a there. So I'm going to get 2 over a denominator that's just exploding in size, right? So the actual value of this limit right here is 0. So I'm getting 5 times 0 and 5 times e, right? The final answer will then be 5 times e. So this integral also is convergent here. Okay? Quick visual on these two integrals. I have the function 8 over x squared plus 4x. And the integral from 1 to infinity is this chunk squeezed in next to the asymptote there. And the 3.21888888 is just the same thing that we calculated as the ln of 25. Next, I've got the function y equals 5x squared times e to the x. Notice one side is tapered and the other side is unbounded. I'm doing the integral from negative infinity up to 1. It's including this little tapered part right here. You just can't really see it. And this entire hump here, and then it stops at 1, which looks like it's the whole thing, but it's not. This thing just ramps up so fast that you can't see that it actually goes really up there really fast. And the integral stops right here at 1. So there you have it. For the last two examples, I want to do the other kind of improper integral, ones that you need to look out for discontinuities of the vertical asymptote kind inside of your interval. Okay? You always need to be aware when you're doing these integrals, because it's easy to just look at an integral and say, oh, let me just integrate this thing and I have two numbers there and just plug them in, and it'll be completely wrong. Okay? If you've got some sort of vertical asymptote, especially that kind of discontinuity in an interval of an integral, okay, you have to treat it like one of these impropers. You have to properly break them down and write out the limit formations, or else you could completely miss something that very well is divergent in nature. Okay, so here I'm noticing that I have a division by 0 if I were to plug in the number 2, because 2 minus 2 will give me 0 in the denominator. And I'm noticing that 2 is the upper boundary of the integral. So I need to accommodate that particular thing. Like so. The limit as a approaches 2 from the left. Notice it's from the left because I'm approaching it from the lesser side. Integral -7 to a of, and I'll go ahead and write this way, 2 minus x to the -1/2 dx. And the reason why I'm doing that is because I'm about to substitute. Okay? So for my substitution, I'm going to let u equal to 2 minus x, which means that du is going to be -dx. I don't have a negative dx, so naturally, in order to make that work, I will throw a negative here, and of course, make the external negative as well, basically pulling a -1 in and out of this thing. Next, I will have negative limit as a approaches 2 from the left. Integral. Now when x is -7, u is 9. Right? Because I'm plugging in -7 here. And this one will be 2 minus a. All right. I am then left with u to the -1/2 du. Right? The negative over here was from the substitution. And then, of course, u took the place of 2 minus x. And negative dx is du. I then perform my antiderivative. So I have negative limit as a approaches 2 from the left. I'm going to have u to the +1/2, right? Because 1 plus 1/2. And if I divide by that, I'm going to get a 2, right? I have to 1/2 divide by 1/2. And then I'm evaluating this from 9 to 2 minus a. Alrighty. So then this is equal to -2 limit as a approaches 2 from the left of 2 minus a to the 1/2. So I'm just going to put square root. Right? That's 2 minus a. Minus -2 times 9 to the 1/2, which of course would be 3. Right? Okay. Well, this particular limit is one of those limits where you can just plug in the number and see that you actually get a function value out of that. In this case, 2 minus 2 being 0, square root of 0 is 0. Limit is completely fine at being 0, right? So this whole piece right here is just 0. And then I have negative, negative, right? So I'm getting 6. Okay? So it is possible for one of these vertical asymptote types of integrals to converge to a number. But you have to be careful and you have to use the correct language in order to make sure that you didn't miss anything. I always have that feeling in the back of my head, right? Maybe I did miss something. I don't know. Okay, so last one. I'm noticing that if I plug in 6, I would get a division by 0. 6 is a big no-no number for the domain of this integral. And I'm integrating from 3 to 8, which includes 6. So the first thing I need to do is split the integral into 2 pieces. Right? I'm going to have an integral from 3 to 6, and plus I'm also going to have an integral from 6 to 8. And of course the integrand is the same for both, 4 dx over x minus 6 squared, 4 dx over x minus 6 squared. Okay? But now we should notice that both of those integrals are still improper. I need to set up a limit as a approaches 6. This one will be from the left because it's from underneath. And instead of 6 here, I will put a. And then plus the limit as b approaches 6 from the right. Maybe B is a poor choice. Let's use C. Okay, so then I will put C here. Okay, so again, it's approaching it from the right because we're coming from the higher numbers on the integral there. So then what I need to do is just perform this antiderivative somewhere so that I know what to expect here. So I'm just going to come down here and do that real quick. The 4 times the integral of x minus 6 to the negative 2 dx. That's the antiderivative that we're doing there, right? I just moved the x minus 6 up. Notice I don't really need a substitution unless you're just looking for that structure. I don't really need a substitution because if I let u equal x minus 6, du and dx are equal, okay? So you can actually just do this antiderivative just like x minus 6 was one chunk in your mind. Du and dx being equal means there's not really any change in the integration, just the way it looks, okay? So the antiderivative of this guy is just going to be 4 times negative 1 times x minus 6 to the negative 1. And of course this one would be, plus a constant if it were just the plain old antiderivative, okay? But we're going to be doing the definite integral, so I'm not really going to be worrying about the constant there. All right. So then I've got limit as a approaches 6 from the left of negative 4 over x minus 6, right? Because that's what this is. And I'm evaluating it from 3 to a. Plus the limit as c approaches 6 from the right of the same antiderivative, negative 4 over x minus 6, evaluated from c to 8. Okay, so here I'm going to have the limit as a approaches 6 from the left of negative 4 over a minus 6 minus, if I just plug in the 3, I'll have negative 4 over negative 3, so just 4/3, plus. Now, I'm hoping that you're noticing that this particular integral right here is already unbounded, right? Because if I plug in 6, I'm getting a division by 0. And from the left on -4 over a minus 6 is a shape that looks like this. Right, where 6 is right here. Okay, the negative gives it a flip of the normal baseball shape, and the -6 shifts it over to 6 like that. Okay, from the left, this thing goes to infinity on that vertical asymptote. So this limit alone right here is infinite. Okay, which is going to throw this whole thing out as divergent. And I know what you're thinking. This is a similar limit over here. Won't they just cancel out? No. No, no, no. If these limits cannot be algebraically combined in general, which we did earlier with a couple of logarithms, and that was okay. Here, they're completely separate, completely different integrals. I split it into 2 different integrals. This being unbounded right here already says that this integral by itself is divergent and undefined as unbounded. Okay? You cannot just assume that the other one is going to have some sort of way of canceling anything out. And you really should avoid the word canceling anyway. Okay? The fact that one of these is unbounded is going to make the whole thing divergent in this case. Okay? Let me go ahead and finish writing it out just so that we can be complete here. I'm going to plug in 8, which is going to give me -4 over 2, which is going to be -2, minus the limit as c approaches 6 from the right of -4 over c minus 6. Okay? And what you should notice is that I can take this negative here, bring it out here, and the value of this limit is infinity as well. Okay? So even still, even if you were going to try and argue the whole cancellation, which you really shouldn't do, there are 2 infinities that are adding together, which is only going to make it more unbounded. Okay? There's no sort of wiping out or evening out here on this one. So overall, I have an unbounded answer. This one is divergent. Okay? So I hope that these examples have shown you the way that you should properly approach integrals that have infinity either as some sort of boundary input or summation output. Either way, you have to make sure and treat your infinities properly, not improperly. So let's wrap up here with these last 2 integrals. Here is 1 over the square root of 2 minus x. And if I integrate from -7 to 2, I have this chunk of area right here, which equals out to 6. The other integral was 4 over x minus 6 quantity squared. And if I'm integrating from 3 to 8, remember I had to split it up into 2 integrals. And GeoGebra won't visually show you any of these, but look at where this asymptote is here. You can see it at 6. And it's just really this huge chunk of area that's just going to go up forever. And notice this reflects it. I have the integral of that function from 3 to 6, which is just this left side of it. That's infinity. And then the integral of g from 6 to 8, which is the right side of it. Both of those are infinite, and it's because of this vertical asymptote in the middle. So if you try to ask it to do the integral from 3 to 8 altogether, it's just going to give you undefined because it doesn't know how to reconcile these infinities.